So we will talk about data pre-processing, but very quickly. Later on we will go back to principal component analysis. But there is an important function which we need to use from sklearn called select k-best. So it's just an example. Do you remember last time when we talk about inseparable data sets? Inseparable data sets, it's hard to find maybe a straight line which can be used to classify those two clusters. And it's important to try to simplify it, to try to put it in a format which can be used for solving this problem. This problem, for example, here, it's a problem in two-dimensional space, and it's easy to find a line, right? It's easy to find a line to separate those two classes into two separate classes. So this one, it's separable, in fact. So this data set, it's separable. This one also, it's separable, but it's in three-dimensional space. So instead of having a decision line as a straight line, we will have a decision line as a plane, for example. Some other data sets, it's impossible to find a line which can separate it into two different classes, and we call it inseparable data sets. When it's inseparable, it's more challenging, and in fact, we need to work a little bit. Maybe you can select a very complex model, but when you are selecting a complex model to generate very complex decision boundary, chances to overfit will be very, very high. And in this case, we need to work with the data set a little bit to try to simplify it. And we had last time very nice example, if you can remember. So I can start. I don't know why when I'm using those when I'm writing. Okay, but maybe I need to clean. So for example, we can take an example, XOR problem, for example. XOR problem, we have two classes, in fact. We have 0 class, we have 1 class, right? And then when we plot it in two-dimensional space, it will be like this one. We have here 1 class in the middle, and outside here we have another class, red class. So we have 0 class, 1 class, for example, the blue one and the red one, for example. So this data set, it's inseparable because we cannot find a single decision line which can divide it into two different classes. So for example, if we need to get, imagine that we can just use a perceptron for this simple problem, maybe we can get a line like this one. So what will be the accuracy of this line? So this one, if we have this blue line, maybe we can get this blue line using a perceptron. And this data set, it's we have 2 input features here, right? So we have 2 inputs, X and Y, for example. And the output, maybe we can call it T, for example. So this is the output T. See, as you can see it here, this model, this simple model, it will generate only this decision boundary. And this decision boundary, maybe it will classify this one correctly. It will classify this one correctly, but those 2 points will not be classified correctly. So if we can check maybe the accuracy, so maybe if this one is classified correctly, this one is correctly, those 2 are wrong. So in this case, the accuracy will be maybe 2 divided by 4. So it will be 0.5 or 50%, right? So this is a problem. So in this case, to classify this problem correctly, we need, in fact, to have 2 lines. We need to generate another line here, for example. So I can plot it with different color, for example. So we need to have 2 lines. So we need to have 2 lines. So all data points between the 2 lines will be classified as 1. All data points above, it will be 0. All data points below the green line, it will be classified as 0. So the accuracy now becomes 100%. So this is the difference between separable and inseparable data sets. So separable, it's a separable if we can, in fact, classify it using one decision line or one decision boundary. So this is maybe this is a model. And as you can see here in this model, we generated those 2 lines, right? And all data points which are located between the 2 lines will be classified as 1. All data points which are above and below it, it will be classified as 0. So in fact, this model's accuracy will be 100%. And of course, just to document the performance of the model, we need to use confusion matrix, as you can see here. So all 0 points, we have here 2. All 0 points are classified into 0. all 1 points are classified into 1. So we can just say that the accuracy is 100%. So please, if you feel that we are going faster, you can just inform me, please. So now I used here logistic regression model. In fact, it's multi-layer perceptron classifier. In fact, for this problem, I used the multi-layer perceptron classifier. This is my data sets. We have those input features. This is the target feature. So this is my sample data set, and we use the one hidden layer with 2 inputs, and of course we have 2 outputs, and we have 1 output. So this one, it's multi-layer perceptron like this one. It will be like this one. So we have only one hidden layer, and this hidden layer has 2 perceptrons or 2 units. We have 2 inputs from the data set. So it will be like this one. Right? So it will be like this one. So this is my model, which we used for solving this problem. I mean, it's a simple model, but indeed also it's MLP. It's multi-layer perceptron, right? So we plot how can we get the confusion matrix. So this is my model. I mean, from STK-learn, we can use MLP classifier. We selected the activation function to be logistic. A maximum number of iterations will be 100. This is the size of the hidden layer. So we have only one hidden layer because we have here only one number. And this number, in fact, it's the number of units here. So we have 2 units in the hidden layer. And we used LBFGS solver or optimizer. And after training the model, we fit the model using our data set. I mean, here, we didn't divide the data into training and testing. We trained the model using all data points which we have. And after that, we used also X for getting predictions. So we have Y predict. If you want to predict model coefficient, you can just get model.coefficient. So to print out the coefficient, if you want to get the prediction error, you can just subtract Y minus Y predict. So in fact, this is Y. This is the actual Y or true Y, in fact, minus predicted Y. We count number of cases where Y not equal to Y predicts, and we get the mean value, multiply it by 100. So this one will be the prediction error. So the prediction error in this case will be 0, in fact. And the plotting the decision boundary, as we mentioned also last time. I mean, this is very nice way for plotting the decision boundary, in fact. So you can just see that, I mean, this is my data set. We have x1 here in x-axis and x2 in y-axis. You just generate values for x1. So we generate values for x1 from minus 0.1 until maybe 1.1. So because I know that my data is located in this range, so we generate all those data points and we create a grid of points, right? For x2 as well, we did the same also for x2 in fact. For x2 we did the same. We have all those values. So in fact we generated a grid of points. So we have all those points. We just send those points to the model. When we trained the model, we send all those points to the model to predict in which class they belong to. So after, in this case, we will get YG, and we just plot it using this contour function, contour plot. So we can just generate it like this one. So we can get this one simply, right? So all points which will be located between those 2 lines, all those points will belong to class 1, and all points above it, it will be class 0. All points below it, it will be class 0. So we can just do it like this one simply. So if you want to plot the decision line, I recommend you to use this approach because it's very simple. So we need to generate all points for x1 with suitable step size. The same for x2. Generate a grid from x1 and x2. We can generate a grid. Send those values to the model for predicting classes, and use a scatter plot or contour plot or whatever. So we can have a nice plot of it. If you want to get the confusion matrix also, we use the confusion matrix from STK-learn in the same way, and the input in the confusion matrix will be the true value and the predicted value. So we have here, those are the true value, and this one, it's predicted value, and after that, just plot it or something, so we can get the confusion matrix. So if you want, I mean, this is the XOR problem. I mean, XOR problem is very important problem, in fact, in basic machine learning, because it just helps people to understand the difference between separable and inseparable data sets. But last time we used more examples. This one, it's XOR like. In fact, it's the same, but instead of having only 4 points, we can just generate a set of points in the same way. So we can just imagine that this one would be class 1, this one would be class 1, this one would be 0, this one would be 0. So it's the same. Just to generate a data set which looks like or XOR. And after that, you can use MLB classifier in the same way. But in this case, maybe you need to make it more complex because we have some overlap between. I mean, they are very close to each other. So we need to generate something more complex. So the curve now, it's not straight line. It should be more complex shape. So if you want to generate more complex shape, we need to have more complex model. So we have the same model, but instead of using the hidden layer 2 units in the hidden layer, we will use 20, for example, or 10. But it's the same. So in this case, we will generate this very complex boundaries between the two classes. So all data points here will be class 0. This one will be 0. All points between will be plus 1.
Can I ask you a question?
Yes, please.
Can we do like the circle? It's like feature engineering before getting these.
Yes, of course. Yes, of course. So if you will go for feature engineering, you will make it simple for the model, right? So I mean, we have those two ways. You can make it. You can just ask the model to do it, right? Or you can help the model. If you can go for feature engineering, you can simplify it for the model. For example, this one way for doing it, for example,
or we could use like the product of these two values.
Yeah, this is correct. So instead of using x1 and x2, we can, for example, use x1 and the other input will be x1 times x2. In this case, you will simplify it. So in fact, you can try different, we call it feature generation. You can generate a new feature, which is a super feature, and it will help you to simplify the problem. So this is very, very important to do, in fact. So one way is to just use the raw data as it is. And in this case, you will make, I mean, the whole the workload will be on the shoulders of the model, because the model need to find this very complex decision boundary. But also the risks to overfit is very high, right? Because the model will be very complex, and when the model is complex, the chances to overfit will be very high. To avoid this, we can use feature engineering techniques. For example, instead of working, I mean, this model, for example, here we have one input is x1, the other input is x2. And this is a target, for example. This is a model. No, sorry, but I can just clean it. This is not the model because it's not a perceptron, in fact, right? I can clean those. So in fact, the model here, it's a feed-forward neural network. So we have two inputs, and we have one hidden layer, which has 20 units, and we have one output. So it will be like this one, right? And we have here two inputs. So chances to overfit may be very, very high. So in this case, it's much better to maybe use different sets of inputs, right? And instead of working with x1 and x2, maybe we need to find a different set of features. So we call it feature engineering. So we need to create a super feature which can simplify this problem. I hope if I have it here, because so. Okay, so for example here, so it's the same problem. So if you will go for x1 and x2, this one is x1 in fact and x2, right? So the problem will be like this one. So in this case, I need to generate something very complex. I need to get a shape like this one, right? So I need to build a model which can generate this difficult or this complex decision boundary. But in fact here, if you can use here x1 and if you can use here x1 times x2, the data set will be like this. So all data points above the line will be class 1. All data points will be below the line will be 0, for example. So in this case, I can just use here, in fact, just a perceptron because I need to get a straight line. How can we get this straight line? A straight line using a perceptron. So just using x1, here x1 times x2, this one is a target. So this model will solve this problem with accuracy equal to 100%, in fact. So do you see? When we change it, when we try to generate a new feature, super feature, we will simplify the model. And instead of using MLB here, we used here simple perceptron for solving the same problem. So if you will use the raw data, you really need to have very complex model to try to find a way to solve this problem, to try to maximize performance and maximize accuracy. But if you can play with feature construction, and if you can try to, this one, we can just call it super feature, right? And it's super feature, in fact, because it helped us to solve the problem very easily. How can we get this super feature? Maybe someone has domain experience. He can just say, okay, I see this problem. If you multiply x1 with x2, you can make it simple. But also, we can just use an optimization algorithm, and we can try different combinations of features. So I have x1 and x2. Maybe I can try x1 times x2, x1 squared, x2 squared, maybe x1 times sine x2. So we can use, for example, an optimization algorithm. We can use genetic programming for doing it, in fact, because genetic programming, you can use x1 and x2, and they can try to make equations from x1 and x2 by multiplications by other operators. Maybe x1 times sine x2, x1 times x2 cubed, x squared. We can find many different combinations, and the optimization algorithm will try to feed those values to the model, and at the end we will get the model with the most simple. Of course, it will take time, but at the end we will have a model which is very, very simple one. Imagine if you have this simple model, it's easy to use it in Arduino. You can put it in each device, for example. So instead of working with very complex model, which will make life more difficult later on, because maybe in the future you want to retrain the model, you want to put the model in an IoT device, for example. How can we use MLP, which has lots of layers, lots of weight values? We need more memory, right? So it will consume more energy, by the way. So when the model is more complex, it will consume more energy. And sometimes you need to put the machine learning model in IoT device, which is running in a remote place, for example, and there is no energy. I want to minimize energy use, for example. So in this case, it's very, very important to try to simplify the model. So this example here, very, very good example, because instead of training, I trained the model here, in fact, using a perceptron. Do you see? We used a perceptron, and we used, this small learning rate, and instead of working with x1 and x2, we used x1 and x1 times x2, and finally we got this very simple model, this one. So and the accuracy here will be 100%. So this is okay, right? So there is no reason, in fact, to build a complex model if you can make it very, very simple one. This example from last time, if you can remember it, so it's the same. We have this, we generated this data set using make circle from sklearn.datasets. We need to generate, maybe blue, I guess blue was +1 and red was 0, for example. We have two classes. And we need to generate a decision boundary which can classify it into two different classes. So this one is x1, this one is x2, for example. So this is very, very complex, in fact. You need very, very complex MLP to generate this decision boundary. But if you can simplify it and somehow to generate this decision boundary, it will be very, very good. I guess last time we had very nice way also for plotting it in different way. So instead of working with x1 and x2, you can try to plot the same data set for x1 squared and x2 squared. In fact, it will be just like this one, right? It will be like this one. When you plot the data in x1 squared and x2 squared, and in this case, we just need a decision boundary which is straight line. Yes. So when we used here x1 squared and x2 squared, we can just get very simple perceptron. We can just logistic regression or a perceptron. Logistic regression, it's like support vector machine. It's linear classifier. We can get this linear classifier from sklearn as well. And at the end, we build a very simple model. And this simple model has two inputs. The first is x1 squared. The second input is x2 squared. The weight here is 8.17. So in fact, it generated a circle. It generated a circle with radius equal 0.91. This one, it's the radius. So this is very complex data set, in fact, very, very complex. It's inseparable. And at the end, we can solve it using a simple perceptron if we can try to play with features. So don't use the raw features and try to make it, try to play with those features. When we have x1 squared and x2 squared, we call it higher order features. Yes. SGD classifier, it's linear classifier. And in fact, it's like support vector machine. It's like support vector machine, and we use it for binary classification problems. Is it possible really to solve MNIST dataset using SGD classifier? Yes, we can try. I mean, MNIST dataset. Do you know MNIST dataset? It's those handwritten digits. In fact, handwritten digits, and each block from those, each image, in fact, it's a 28 times 28 pixel. 28 times 28 pixels, and I guess we have 60,000 images for training and 10,000 images for testing. So you can get this one from also sklearn datasets. You can get MNIST dataset, and here I try to solve it using. I mean, we have 60,000 data points for training and 10,000 data points for testing. So I solved this problem, in fact, using SGD classifier, and we have this results here. We have this results here. I will talk later on about what is the meaning of precision and recall, because those numbers are very important, right? So you need to have this table. I mean, it's recommended to have those numbers all time with your problem, right? It's not binary classification problem. So in fact, when it's binary classification problem, it's easy to understand the meaning of precision and recall. But when it's multi-class classification problem, we need to get precision and recall for each class. And those numbers should be the average, in fact. Those numbers should be the average. So this problem, we just used a model called the SGD classifier. You can, I mean, and we trained the model using X-train and Y-train. We use the X test for predicting, so we have Y predict. We can use those Y predict and for getting precision score, right? So we have this one. It's a true labels. This one, it's predicted labels. When we use macro, when we use this one here macro, it means we get average precision, right? Because this problem, it's multi-class classification. What does it mean, multi-class classification? In this problem, in MNIST dataset, we have 10 classes. Do you remember? We have 0, 1, 2, 3 until 9. So in fact, it's multi-class classification. And we should, when we are getting a precision and recall, we should get precision and recall for each class. So for this class, we can get precision and recall. For class 1, we get precision and recall. For this one, and so on. So in fact, when we use here macro, I mean, this value will be the average. In fact, when we select average equal macro, we will get the average value for all classes. So we have precision recall for training and for testing, right? And after that, we can plot also the confusion matrix for training and for testing. Maybe it's very, very important for testing, not for training, right? So we need to have the confusion matrix. How can we get the confusion matrix? We have also a command called the confusion matrix, and the input to the confusion matrix will be the true labels and the predicted labels. True label and predicted label. You will get this matrix. And in this confusion matrix, in fact, we are interested in this diagonal. All numbers on those diagonals, those are the true, how can we call it, true positive, correct? So for example, this is how many 0 letters are classified as 0, this number. This one, how many 1 classified as 1, how many 2 classified as 2, correct? So in fact, we are interested to increase the true positive values because those are the true predictions, correct? So we need to increase all numbers across this diagonal and try to minimize those numbers, because those numbers, in fact, those numbers are false. It's like false positive, false negative, right? Because those numbers are misclassified. So this 6, in fact, it means 6 zeros classified as 2 or misclassified as 2, right? This one means we have 4 zeros classified as 5. This one, it means we have 5 zeros classified as 4, right? So in fact, we are interested to maximize all numbers across this diagonal and minimize all other numbers. If we need to get accuracy, we need to sum all those numbers and divide it by the total number of training, the size of the training set. So we need to sum those numbers and divide it by 10,000 to get accuracy, right? If you want to get recall and the precision, I will discuss. I will talk about recall and maybe in the next slides. So, I mean, last time we got. I have a question. I mean, I mean, in this example here, we divided the data into training and testing because we have a large data set. In fact, we have 70,000 data points. So we divided it into training and testing. So in this case, we used the hold out validation, right? We used here hold out validation. But what should we do when my data set is small? So when the data set is small, we cannot use hold out validation, and we need to use cross validation. In cross validation, how can we use cross validation from sklearn? We just need to get this command here. From sklearn model.model selection, we need to import cross validation score. And in this cross validation, in fact, we need to define a model. First, I need to define my model, right? So we just defined my model as we do all time. I have a model. For example, I selected SGD classifier, and I mean, this random state, we define it because maybe each time I want to have the same initial values, because I will use this model several times. So each time I want to get the same random values, initializing my weights with the same random values. And after that, I will use this cross validation score. The input to this one will be my model, right? My data set, my whole data set. We don't need to divide it. So I need to have X, Y. So X are the input features, Y are labels or target features, and this one it's a k fold. How many folds? How many k folds? Or this is k value. So when you select a k equal 5, in this case we will divide the data sets into 5, right? And you need to select what scoring you want to get. So I'm just selecting accuracy, for example, right? So in this case, we will divide the data sets into 5 blocks, right? We will divide the data into 5 blocks because we selected k equal 5. I will train the model with 4 and test with this one for the first time. So I will do this one. I will train the first model, this model with 4 folds and test it with fifth one, and I will get an accuracy. It will be this accuracy, right? When k equal 2, I will train the model maybe with this one, this one, this one, and this one, test it with this one, and I will get another accuracy. And I will repeat this process for k equal 5. So we will get, in fact, at the end, 5 accuracies, one for each model. And in fact, each model, each time, we reinitialize the model by those, we initialize the weights with the same random values. So each time, in fact, I have a brand new model, right? And at the end, I will get 5 accuracies. So at the end, the output from this one, it will be the average accuracy. We will get this average accuracy at the end. So if you will use this model using a cross validation, you will get this kind of average accuracy at 91%. As you can see here, sometimes it's 91.3%, sometimes it's 91%, sometimes it's 90%, sometimes it's 92% each time, right? So the average value will be 91%. So in fact, when it's average, it's a more robust value, more reliable. So now I finished the cross validation. At the end, in fact, after finishing this one, now I have an average accuracy. So after that, you need to retrain this model one more time because this one will be your model, right? You cannot select this one because this one, it's much better. I cannot select this one from cross validation. I cannot select this one. No, we use cross validation to make evaluation for the model, in fact. So now if I selected a model with this specification, I guarantee that if you will use cross validation, I guarantee that you will get an average accuracy of this value. It's recommended also to calculate standard deviation, in fact, right? Because if you can see here, this is the mean value, but this mean value, it can go up and down, right? With some standard deviation. So when you are writing it in your paper, in fact, you need to write average accuracy. You need also to get standard deviation. This is very important to be more professional because there is no guarantee that we will get this value, in fact. We will get this value, but plus minus some standard deviation, correct? So this is very important. When you are documenting it in your results, you need to write the average accuracy plus standard deviation. This one can go up and down with this in this range. So after that, I will retrain this model using, so at the end, I will just say, okay, model dot fit using X and Y, whole X and Y. Now we didn't divide the data, in fact. This one will be the model which will be deployed in real life. I don't need to test this model again. We don't have data for testing it, and we have been testing it, in fact, using a cross validation. Yeah. Yes. So after training the model, we will get this average accuracy. I don't need to train the model anymore because we have been already evaluating its accuracy. But just remember to calculate also standard deviation. We have very simple function. This one, similar to this one. This one, SEC, it will be scores, all those scores. You can get the mean value. You can get also standard deviation. So you need to print those numbers, right? To look like, professional. If you want to have, if you have to get the confusion matrix for training, for testing, it's fine, but not maybe for training. I mean, as you can see here, this one, I don't know which one for predicting, which one for training and testing, but anyway, maybe it's more important for testing, for training. But in this example here, in fact, remember, in this example, we use the cross validation. We don't have any testing. We don't have any testing anymore, right? So you can do it for the whole data set, for example, if you want to just look to see which one has been. But also, it's important to get precision and recall. Those values are very, very important. And we have command precision and recall. This one. So we have this precision score. The input to the precision score and recall score, it will be the true labels and the predicted labels. And you need to select this one. And when it's macro, you will get the average values, right? I guess when it's a none, maybe it's weighted or something. I mean, it's macro, weighted. So we need to check it, in fact, in scalar. Yes. Do you have any question for this part? Any questions? Should we go for feature selection? Because now we talk about feature construction. I mean, feature construction here in this examples, feature construction. I mean, you can construct it if you have the domain knowledge, in fact. So if someone has the domain knowledge, you can directly construct some features. So there are some algorithms for feature construction. And those algorithms, in fact, it's like genetic programming. It will try to make many different combinations of my features and the test using statistical tools to test correlations between the new feature and the target, and just say, okay, this new feature looks amazing. So there are lots of tools, in fact, for feature construction. For feature selection, it's also important because sometimes we have lots of features and we don't know which features are more important. So this is the problem, feature selection. We need to select the most important features, and they are useful because sometimes we have some redundancy, we have some correlation between features, so there is no meaning, in fact, to use all features. So imagine, for example, you want to get loan from the bank, and they want to ask about years of experience, age, maybe, and maybe education. I guess there are some correlation between age and education, for example. So if we are old, maybe we finished the PhD already, we have more years of experience, so they are correlated. So maybe age and years of experience, not very important. We need to select only one. So those feature selections, the idea behind it is to try to select the most important feature, so we can try to simplify the model. At the end, simplifying your model is very, very important to avoid overfitting. We can just use the whole set. If you use the whole set, maybe it's too much, it's not very important. All those features are not very important, and we need to select the most important features to make the model less complicated, and the training process should be less complicated, and in this way we can try to avoid the problem of overfitting. So feature selection, it enables the machine learning algorithm to train faster. So it will just train faster, very quick. It will reduce complexity of a model, and it makes it easier to interpret, improves accuracy of model. If the right subset is chosen, reduces the chances to overfit. And remember, if you need to have a machine learning and you need to put this machine learning in IoT device, for example. So those those edge devices, they have some limited capacity, in fact, small memory, energy consumption, and so on. So it's very important to simplify the model. If we need to simplify the model, we need to select the most important features. not all features are relevant, in fact. So there is nice tool. I want you to check it, in fact. It's called Select K-Best. It's from sklearn, in fact. So in sklearn, we have feature selection toolbox. From this one, you can import Select K-Best, for example. Select K-Best. It's Select K-Best features. So I have a set of features. Maybe it's N, for example. This one will select the most important. You need to specify. So for example, I have N, and I can just say I want to select the most important 2 features or 3 features from those N features. And it's based on statistical calculations. So for example, you can, here, for example, someone can select chi-square, for example, or some other people can select other things. I mean, here in my computer here, you can select many things, in fact. So for example, you can select chi-square, you can select F regression. So there are many options we need to test. But this function is very, very important for feature selection. This one is very, very important. So it's a univariate feature selection based on statistical tests, and it removes all but the key highest scoring features. So from this one, you will have this select K-best. You have all your data points here. You can just get a subset from those all features. We have N features. Maybe the output here will be maybe K features. I select K features. So this one is very, very important. So if you want to use it, I used it, for example, with Iris dataset. I mean, in Iris dataset here, we have 4 features. Do you remember how many features in Iris dataset?
Sorry, how do you know how to choose this function, square or Fisher?
Yeah, it's chi-square or Fisher scores. You need to try. I mean, what is the difference? Just to try, what is the difference between this one? It has a meaning in statistics. It has some meaning in statistics. So, for example, if you will use chi-square, the scores, maybe, I mean, it's maybe little difference, in fact, between those approaches, but it's statistical approach. So you need to select. It could be like a hyperparameter, for example. Maybe you can try one time chi-square, another time Fisher score, another time another approach. So you can try all different types. I mean, in the next slide, I will talk about the pipeline, and then when we build the pipeline in machine learning, it will make life more simple because we can try different combinations of hyperparameters. So here I use Iris dataset. In Iris dataset, we have in fact 4 features. We have x1, x2, x3, x4, right? It's better length and width, and the sepal length and width. And I want to select 2. Here, I want to select 2, the most important 2 from those ones. So in fact, we need to select, we need to start a selector. So the selector will be select K-best. I need to specify the score. I used here chi-square. And also I need to select K, what K value. Also, it could be hyperparameter. So maybe someone can test 1, 2, 3, because each time you will get different accuracy, right? So if I have 4 features, maybe I can try to select 1, 2, 3, for example, and 4. So I can try all different combinations. And after that, you will fit the data X and Y. Y is very important because it calculates correlation, in fact, between each column and the target, right? So it calculates the correlation between each X value, each feature, and the target features. And after that, you will get those numbers. Do you see? This is the score, in fact. So after that, we can print scores. So selector.scores, so we will get those scores. So those are all scores. Those are all scores of all features. We have 4 features. So for x1, it was 10.1881. For x2, it was 3.7 correlation. It was for x3, 116.3. For x4, it should be 67.04. And it's clear that we should select if we need to simplify the model, and if we need to select the best 2 features. In this case, we need to select x3 and x4, right? Because this is correlation. So this tool is very, very important. So now instead of building a model with 4 inputs, I can select a model with 2 inputs. And based on chi-square scores, I can just select x3 and x4. So now it's much easier for us. So now, we can just use maybe beta length. and the petal widths are more important than sepal length and sepal width. So in this case, we will select those. Yes. Yes. So any questions in this feature selection? Because the next step will be feature reduction or dimensionality reduction using a principal component analysis. But we have some difference between select k-best and dimensionality reduction or principal component analysis, in fact. Because this model, I mean, when we use select k-best, in fact, we just find the correlation between each feature and the target, and we select the most correlated features to the target. So in fact, the input will be features, the output will be the same features. So we have here input x1, x2, x3, x4. The output from this one, it was still x1, x2, x3, x4, but we will select x3 and x4, but they are still petal length and petal width, right? So we understand them. But in case of principal component analysis, it's different, in fact. I mean, the outputs are not the same as inputs, right? Because the output will be principal components. So for principal component analysis, we will use the inputs here will be our features. It's x1, for example, x2, x3, and x4. But the outputs here will be different, in fact. It has different name. It will be principal component 1, principal component 2, principal component 3, principal component 4. It's the same dimension. So the input were 4 values or 4 column. The output will be 4, but the meaning of those is different, in fact. So maybe this one, it's length and width in centimeters or in millimeter, for example. No, the outputs are different, in fact. It's not does not have any meaning, in fact, because it's the eigenvectors and eigenvalues, or eigenvector. You can say that it's the principal components or is a projection of the data points in the direction of the eigenvectors. So it does not have any meaning. And we need to keep this one with us all time. So if you will train a principal component analysis, you need to have this one with you all time. When you are getting data from outside, for example, maybe you are collecting data from sensors. So the data coming from the sensors, it must go through the principal component, this one. So we can convert those inputs into, for example, if we will select the principal component 1 and 2, you must convert those numbers into BC1 and BC2. We will have here a transformation matrix. We will get here a transformation matrix. We need to keep this transformation matrix with us all time. And all time, you need to multiply the raw inputs coming from outside by this transformation matrix to get those principal components. Because we will train the model using the principal components. And the principal components does not have any physical meaning. So it's not measurements, it's not weights, it's not speed. So for example, if you are collecting speed, temperature, weight, current, voltage, right? So when we apply it to principal component, we will get different numbers here. Those numbers, in fact, does not have the same physical meaning. So we need to keep this transformation matrix with us. This is a drawback from principal component analysis. We need to have this transformation matrix with us all time. So if you want to put your system in Arduino, for example, you need to have enough space, enough memory for having this transformation matrix with you all time. And when you are getting raw inputs from outside, you need to multiply it by this transformation matrix to get this principal component.
It's like from getting from time domain into the frequency domain.
No, it's a projection in the direction of the eigenvectors, right? So, for example,
it's something like that, the projection from one domain into another domain.
Yes, it does not have the same meaning. So, for example, maybe I have a data point like this one, right? So this one, it was x1 and x2. I'm collecting data x1 and x2. So the eigenvector will be this. The eigenvector will be this one. So the first eigenvector will be this one, right? Because we have lots of distribution across this one. I mean, the variance across this eigenvector is too much. So this one will be, I call it theta 1, for example. And the second eigenvector will be perpendicular. So it will be like this one, right? So it will be theta 2. So after that, we will transform the data. So the data will be represented in this new domains, theta 1 and theta 2, for example. And it will be just like this one. You see? It will be like this one. So it does not have the same meaning. Maybe x1 here, it's temperature. Maybe if you are measuring temperature, maybe x2, it's maybe weight or speed. No, those ones will not have the same meaning. Does not have the same meaning. To convert this one into this one, we will have a transformation matrix. So all data points will be multiplied by this one to be transformed into this one. So this transformation matrix, we need to keep it with us all time. And when we train the model, in case of principal component analysis, we will train the model using principal components. So the model does not know anything about x1 and x2. So it does not understand it. So all values which you are getting from outside must be transformed into those principal components first. So how principal component works? It's also very simple. I mean, it's a very simple here. We need to use also principal component from sklearn.decomposition. We can get this principal component analysis. And in the principal component analysis, we have very important factor which we need to decide: number of components, how many components you want to get, right? So for example, I used it here with MNIST dataset. In fact, so MNIST dataset we have 28 times 28 pixels, right? Can you multiply this number, please? 28 times 28. So 28 times 28. So it's 784. So we have 784 features, right? So we need to specify here number of components which we need to keep. We need to reduce those 784 to a small set or a subset of features. So we need to decide here number of components. How much reduction? It's number of components divided by 784. If you need to see how much reduction. So for example, here in this example, I'm selecting 8 times 8, which is 64, right? So in fact, how much reduction we can achieve here? It would be 64 divided by 784. Can you see how much percentage?
3%.
8%. So it's
92%.
8.2%.
It's 8.1%.
0.1%. So it's 8.1%. So we reduced the data from 100% into 8.1%. So we reduced it by around 92%. In fact, when we use the principal component analysis, I didn't use all features. I just used 64 features instead of 784. So there's a huge reduction. In fact, we call it dimensionality reduction or compression. In fact, data compression, right? We compress the data. And then when you compress it, so instead of building a model with 784 inputs, we will have a model with 64 inputs. So now it's much simple, right? It's much easier to build a model, train a model, test the model. It will make our life much, much easier. And to convert, because all images which you are collecting, imagine that we are building a system which will take images, capture images from roads, for example, and we need to analyze those images, make decisions, read the car plates, right? So in this case, we need to have, after this transformation, we will have a transformation matrix. We need to keep this transformation matrix with us all time to convert raw data into reduced set or reduced data or compressed data. We will train the model using the small set 64, not original one. So each time we need to convert the original one into the small set. So you need to specify this number of components. This number of components, it could be float number between 0 and 1, and it means ratio of variance you wish to preserve. So for example, I know that the variance in my data set can be reserved by 100% if I will use all data points. But maybe you can just say, no, I don't need those 100% variance. I need to keep only 80% or 70%. So in this case, you can just select any component equal 0.8 or 0.7 or 0.9. So I need to find number of components which will give me, for example, 80% variance. Keep information, for example, you can just say how much information we need to keep. Do you know when we compress data, we lose something, correct? When we compress anything, we lose some information. So in fact, here we will lose some information, but the value or the trade-off of complexity, I can just simplify my model. I can have a model which is more simple. So we need to specify number of components. This number, it could be float number. So it could be 0.7, it could be 0.6, and this number will represent ratio of variance you wish to preserve, how much you want to preserve. Or you can select an integer number, and this integer number will be the number of components which you want to get. So here, for example, I selected n component equal 64. So in this case, I don't know how much variations we will preserve. We need to check it. And after that, you can fit the model with x, only x. Do you see this one? So I define the BCA, and after that BCA.fit using x, only x, not y. Do you see my data set has x and has y, but we focus only on x, on the feature, which
it means that this procedure is blind. It's like a blind software.
No, it's unsupervised. You can just say it's unsupervised,
yeah, it's unsupervised,
right? Because we use only input features. We don't use target features, so it's unsupervised. You can get also how much explained variance ratio, and you can get also cumulative sum, and you can print very nice graphs. I mean, anyway, I will go back to this one again in the next slide. So because maybe you need to get some break. So quickly we will take a break. Yes. So this one, it was the original image. Do you see this one? This one, it is the original images. And each digit, in fact, it's represented by 2820 times 28 pixels. So everyone like this one. So this one, in fact, has 28 times 28 pixels, which equal 784, I guess, inputs. So if I want to build a model, in fact, if I need to use MLB for this model, I need to build a model with this number of inputs. So the model will be really very complex. How many hidden layers? The model also, the number of units in the hidden layer should be greater than this one. I cannot have a model like this one. No, but the model should look like this one. So this one will be number of inputs. If I have hidden layer, I need to have more numbers here, and after that I need to have the output here, right? So it will be very, very complex one. And I don't know if we have enough data really to train this model, because if you don't have enough data, chances to overfit will be very, very high. So this is the original one. When we use principal component analysis, we can compress this one into this one. This one, it's reconstructed. Those images are reconstructed using 144 principal components. And you can still be able to identify that this one is still 0, this one is still 5, this one is still 2, this one is still 1. So in fact, it was not very important to have very high definition images, and it was useful to try to reduce or compress data from its original form into this one, in fact. This 144, which means the 12 times the 12, correct? So in fact, each one here, it's 12 times the 12 pixels, right? So we reduced it from 28 times the 28 into 12 times the 12 pixels. And we're still able to recognize each digit. How do you need to, how can you reconstruct it? Just here, you have, when we trained this principal component analysis, we trained it using X values. And after that, we can convert X into reduced X, right? So this is the input, and we convert it into this reduced one. And this reduced one, you can recover it, in fact, also into, you can use this command for recovering it or reconstructing it one more time. Yes. So we will select only 144 principal components. You can just convert this one into matrix notation, put it in matrix notation, and try to plot it again. So you will get those images. So finally, I will try to train this classifier using the small set or a subset. So instead of working with the whole data set, I'm training it using 144, right? So this is my data points. I have X train, Y train, which already divided, and I will select SGD classifier. SGD classifier, I will train the model using X train, Y train, and X test. So this is the original, in fact, this is the original model. This is the original model, and this is the accuracy, and this is the confusion matrix. This is the accuracy. I don't know which one was reduced, which one was not reduced. I guess this one it's reduced using 144. This is original, right? So maybe you need to go to the code. You need to go to the code to get the rest of. So in fact, we are converting x into x reduced. So here we should use x reduced, not. So after getting x train and x test, for example, right, and y train, I mean x is the most important. I need to use the BCA here to get reduced, the compressed one. But maybe I didn't copy all. I didn't put all stuff here. Yes. So I because now it's 1 hour, so I'm sorry for we need to take maybe 5 minutes or 10 minutes break and start back again. But before leave, do you have any question for that part? I mean, we will go back into those again and again because I mean we have one lecture, in fact, for unsupervised data sets, and in unsupervised data set, we will try to talk again about principal component analysis and also autoencoder, because we can use autoencoder and the principal component analysis for dimensionality reduction and data compression. So we will go back again, in fact, to both of them.
Is there any supervised method for this suppression of features?
I mean, for selection, I mean, this selection, you can say it's supervised because we find a correlation between inputs and outputs. So when we use this select k-best, it's very important to have y here, right? Because it's a statistical approach, and we try to find the scores or correlation between features and the output. So we need to keep the output. So we can consider this one as supervised.
Maybe autoencoders are also like kind of supervised.
No, autoencoder is unsupervised.
Oh, they are.
Autoencoder, it's in fact it's a feed-forward neural network, which is supervised, but because we are using only X, we don't use targets, so they call it unsupervised. But in fact, we use error backpropagation, and we use outputs. We train it as a feed-forward neural network, which is supervised. But instead of having this prediction error, we call it reconstruction error. But because we used only X, they call it unsupervised. But internally, in fact, when you train it, it's supervised, right? Because we have the error backward and we train the model. So, but instead of using prediction error, we use something we call it reconstruction error. Yeah. So we will take maybe 10 minutes break, and we can start, or 5 minutes. It's up to you, and we can start again after maybe 5. You can just get your coffee, for example, and we can start again after 5 minutes. Yes, thank you very much.